Okay, good afternoon, everyone. I'd like to welcome you all to the third UK Fluid Mechanics Conference. My name's Oliver Jensen, and my co-host, the other principal organizer is Raphael Assier, who should be here somewhere. There he is. So if you have any sort of urgent questions, please ask either of us. We're all obviously very glad that you're here and looking forward to a very interesting few days. I've got a few things, bits of business to tell you about before we start. But just sort of by way of introduction, of course, I couldn't not mention all the sort of distinguished fluid mechanics people associated with Manchester, going back to Osborne Reynolds and Horace Lamb, Sidney Goldstein, James Lighthill, Fritz Ursel. So we're very proud of our heritage here, so very glad you're able to share a bit of that with us today. For those who don't know, the current university came into existence in 2004 through the merger of the old Victoria University of Manchester and UMIST. So it's a very large institution, and currently fluid mechanics in Manchester is spread between engineering departments, engineering schools, mathematics, and physics and astronomy. So it's another great opportunity for us to sort of come together as a fluids community here with you all. We've got 230 plus delegates here, which is a record in the very short life of this conference. But I think it's a great sign of the vitality of this area. We've got over 120 short talks. We've got 4 fantastic plenary speakers. We've got a couple of longer talks at the end of the conference from winners of the UK Fluids Network Thesis Prize, which you can hear on Thursday. And then we've got almost 50 posters as well. So we're very sorry that we couldn't accommodate everybody's desire to speak. I'm sure you understand we have, there are a few constraints, but plenty of time to look at posters outside. There's a poster reception this evening, of course, and the posters can stay up overnight and all through tomorrow. If you do have a poster up, we can't guarantee the boards will still be here on Thursday, so please make sure you take it down at the end of business tomorrow. The program is online. Of course, since we went to print with the program, there have been 1 or 2 changes. I'm afraid we've had some very late cancellations, which I've written up here, indeed, including 2 in the first sessions this afternoon. So in session S1 at 3 o'clock, 15:02, and another one in S2 shortly after that. That's 1542, not 1502. 1542, the first one here. We will just have a pause in the proceedings in each session, so we won't adjust the timetable in any way, but this is just so you can beware in case you were hoping to hear any of those speakers. As is traditional at this meeting, we're using a timekeeping system. It's actually very important because we've got a lot of talks to squeeze into a very short time. And so we've got this screen here which will flash different colors and count down. So for those of you who are giving 10-minute talks, okay, your session is 12 minutes. Please aim to speak within 10 minutes, and then we'll have 2 minutes at the end for questions and the next person getting ready. And the screen will go from green to yellow to red to black. You'll see the pattern, sort of more and more ominous colors. And if it's black and you're still talking, you should shut up and let the next person get ready. Okay? And the chairs will help you through all that. We're very grateful, of course, for this meeting for the support from the 2 Centres for Doctoral Training in Fluid Mechanics at Imperial and in Leeds. It's a great initiative that these 2 centres started, and we're very happy here in Manchester to continue it. And it will happen next year in Cambridge and thereafter somewhere else. So I think there's a great opportunity for this to become a really well-established event, independent of any CDTs in the longer term. We're also grateful to our sponsors, and please look at their desks outside. In particular, the UK Fluids Network and the Journal of Fluid Mechanics are sponsoring prizes. There are prizes for talks, prizes for posters. So you might, if you're looking after either a talk or a poster, you may be visited or watched by some judges, so beware. In fact, the poster vote, of course, is a popular vote, so you should have picked up a leaflet which you can use to make your vote for the best poster. There shouldn't be any fire alarms. if anything happens, if it's a continuous alarm, just please get up and leave the building out this door here and gather outside under the arches. There's dinner tomorrow night. That's going to be in the big Sackville Street building just across the road. So please, if you've signed up for that, please make sure you bring your ticket with you. Let me see. Toilets, just in case anybody wants to know, you go back out to the foyer here, and then downstairs, down the stairs at the end, there are some accessible toilets there. Two other things I want to mention. We have this lecture capture technology here, so the talks will actually all be recorded. The audio will be recorded, and the image will be recorded. And we'd like to make those available as podcasts afterwards for people who couldn't be here. If you object to having your talk being podcast, please just give your name into whoever's manning the registration desk, and we'll make sure it's edited out. But I hope people will be happy to have their talks available for people to listen to later. And the other thing is that there is going to be an opportunity at the end of the week, at the end of the meeting, right after we finish, at 4 o'clock on Thursday, for a small number of people to go and see Osborne Reynolds' original pipe flow equipment, if you're into that kind of thing. We all learn about it. So we can take about 40 people to go and visit the lab and see that equipment. So we'll put a list at registration for you to sign up for that if you'd like to do that. And we have one or two helpers in purple T-shirts so you know. Oh, you see, I'm already getting warned. Okay, so I think this is at the right time for me to hand over to Nico, who's going to introduce our first plenary speaker. Thanks very much.
I better go over here. I'm just, yeah. So it's a great pleasure to introduce Olivier Poulican, who is a very distinguished scientist who 20 years ago got into granular materials, which he's originally a fluid dynamicist, but he got into granular materials. And he, you would sort of think granular materials are not fluids, but they can behave like fluids. And Olivier did some very simple but very insightful experiments, which started off by showing for avalanches down rough boundaries what the friction law was. And it was a generalization of Coulomb's law that ultimately led to the development of a full tensorial constitutive law for the fluid-like regime of granular flows. And that insight that he had has completely revolutionized the subject of granular flows, which has sort of been notoriously a very difficult area of research, and his work has set the agenda in that area to the present day. And so it's going to be interesting to hear from him. Over the years, he's sort of moved on from the granular materials. Or he's still doing granular materials, but it's sort of developing. So the law that he found was essentially a complex fluid where the viscosity was pressure and shear rate dependent. Oops, I should be quiet. And so he's taken that on and he's gone on to suspensions, and now he's headed off into looking at how plants are governed, or the growth of plants is governed by granular flows.
Okay, did you hear me? So thank you very much, Nico, for this nice introduction. And many thanks to Oliver and Raphael for the invitation to be here with you, although I'm not from UK, as my accent will tell you. So today I'm going to tell you a story about fluid mechanics, granular material, but at the frontier with soft matter physics and biology. And I'm going to speak about how plants feel gravity. So that's mainly a work that we have done in Marseille and in collaboration with people from Clermont-Ferrand, which are biologists. So everybody knows that plants grow up to our... So I just start early. So everybody knows, yeah, that plants grow up against gravity. So, and that's true for small plants like this one, Arabidopsis, which is the model plants for biologists. But it's also true for trees, as you can see here in this beautiful picture that comes from a Polish forest. So it's not natural. Huh? People at some times are cut a little bit of the trees, put them horizontally, and at the end you find this beautiful shape here that is here. So this is not, start with that, this is not due to light. Of course, plants are sensitive to light. They want to go towards the light. But here, for example, this experiment is done in the dark without any light, just for the flash, for the picture. And so that means that the plants have the ability to feel gravity and to know where is the top. So this is well known for quite a long time, and Darwin was the first, in fact, to try to understand what is happening. And so the basic gravity sensor is known. It's specific cells that are called statocytes, which are both in roots and shoots, because roots are going down and shoots are going up. So in roots, they are localized at the tip of the roots, and in shoots, usually it's close to the epiderm. There is a kind of layer of those cells. And they are specific because they contain starch grains, about between 5 and 10 microns, which are heavier than the surrounding fluids in the cell, and so they sediment, and that's what is supposed to give the direction of gravity. So you understand now why, coming from granular material, we get interesting in this kind of systems. So that's the sensor, and the main picture, the main scenario that you can find in the literature is the following: that when a plant is inclined, for example, you have a motion of those grains, and this motion of the grains through some kind of biochemistry reaction induce some flux of an hormone, the auxin. Auxin is a growth hormone. And so this motion of the satellite induces asymmetric flux of hormones between the top and the bottom of the plants. And so it's a growth hormone that's induced a differential growth between the top and the bottom of the shoot, of the stem. And a differential growth between here and here create curvature. And so that's how the plant is able to curve and to bend and to go back to the vertical. So if this main picture is well known and well accepted, there is a lot of open question within this picture. First, about the sensor itself. Nobody really knows how it works. And for example, what is detected in those cells? Is it the position of the grains? Is it the weight of the grains? Is it the motion of the grains? It's not clear, and there is papers saying everything in the literature. Why a granular sensor? Because it's coming from the granular community, it does not seem to be a very sensitive sensor. And also the link between what happened at the cell scale and the plant scale is really not clear in the literature. So that's why we start to work on it. And just to tell you about, for example, even without looking at the sensor, the response of the plants itself at the macro scale is not clear also. So basically what you find in the literature is two famous laws. So that's called two famous laws of gravitropism, but which seems to have nothing in common. We have first what is called the sine law. So the sine law is what? Is some measurement, and there is not really a lot of measurements. That's really amazing. That stipulate that if you take a plant, you incline it at a given inclination, theta, the response of the plant in terms of the velocity at which it will come back to vertical is proportional to the sine of the inclination. So that's why it's called the sine law. On the other side, you have some other papers that talk about a dose-response law. But the experiments are not at all the same as those one. Dose response is people who have done our work in microgravity. And they were interested in trying to find what is the minimum gravity detected by plants. So what they have done is that you incline the plant, you switch on gravity by centrifugation in microgravity environment during a time delta t, and then you switch off gravity. And what they have found is that the response of the plants, again in terms of velocity of bending, seems to be proportional to the product of the gravity times the time of stimulation. So a kind of dose that is filled by the plants. And so first, there is nowhere any discussion about the link between those two laws. And what is the physical origin of those two laws is not clear at all in the literature. So that's all the questions that are here about this gravitropism, and that's where we start our work. It was about 5 years ago, trying to understand, in fact, what is a sensor and can we learn something about the response of the plants from what we can learn about the sensor. So we have done two kinds of experiments, you will see, both at the cell scale and at the plant scale. So let's start with our first experiment, which was at the plant scale, just to learn about this gravitropism. And you see here a beautiful movie about typically what we are doing. So the model that we are using here is just with coleoptile. So it's very simple, but it's just a stick. So just in terms of image processing and so on, it's very simple to analyze this kind of plants. So everything, all the experiments are done in the dark in order to get rid of the light. So it's just gravity that is studied here. And the first thing that so here it's accelerated in this movie, that we are doing is just first change the inclination angle of the plants and measure how what is the spatio-temporal dynamics of the bending. So typically that's what you get, and you easily extract the skeleton of the plants and find the spatio-temporal dynamics. And you can extract from this the growth rates. You just measure the length because the plant is living, so it's just growing. And what is interesting that we're measuring the tip angle of the plants, which is increasing and come back to 0 to reach the vertical. And in fact, we can show easily that what we're interested in for the gravitropic response is the difference of growth between the top and the bottom. And we can easily show that this is related to the time derivative of the tip angle, how fast it's come back to vertical. That's really related to the differential growth. More specifically, more precisely, you have to divide this by the growth rate because that's the only time scale you have. And that's what the response, the interesting response you have to measure. So from this, we can measure the response of the plants and measure it for different inclination angles. So the quite first easy experiments. And that's the main results that we get. We find, again, the famous sine law, the fact that the plant responds faster. It's biology, coming from fluid mechanics. It's not easy experiments, and you have a lot of noise, but that's life. And so you see that the response is faster at 90 degrees. So if you put the plant horizontally, that's when it's bend more rapidly. And that is go to 0 at close to 0, and go to 0 when you put the plant upside down. Okay, so that's quite more precise, perhaps, measurement, but that's something that was in the literature. And if you go in textbooks, in fact, you find the sine law, and some explanation of the sine law is very simple. They just say that the weight of the grains of the statolite inside the cell, by just the lateral component of the weight on the side of the cell is just mg sine theta, and that's why when you incline the plants, you measure something that is proportional to the sine of the inclination. So, okay, if this is true, that means that this law is not a sine law, but it's a G sine law, and that's the first thing we wanted to test. And that's we start by taking our rotating table, put all the plants on the rotating table, and that's a way to create an artificial effective gravity which is higher than the Earth gravity, and to impose the plants to this Earth gravity. Of course, the direction of gravity also is changed, but you just have to measure the inclination relative to this new direction. So just to tell you that it works, that's an example of a picture that you have when you let the experiments going on with that's not width, that's lentille. But you clearly see here the direction of gravity. That's quite a nice picture. So that's the rotation center was here, about here, and so the box is rotating like this. So we can do the same kind of measurements. And that was our first surprise in the story. That's the response of the plants at 2.5 G here seems to be exactly the same as 1 G. That means that the intensity of gravity seems to play no role in the response of the plants. So another way, so we did that. So that's the response in terms of the rapidity of bending divided by sinus theta, now that we know that the shape is a sine. And you see that as a function of the effective gravity, and you see that between 1G and 3G, there is absolutely no influence of the intensity of gravity. So that's the first result. Of course, in biology, people want to show universal things, that's just with width. So we had to do the same kind of experiments, which is not, which is quite a lot of work, on different species coming from different branches in the phylogenetic tree. So we did that on wheat and lentille, in Arabidopsis and in peas here. And in all those cases, we see that we have no influence of the gravity intensity on the response to gravity. So that's the first result, but which has strong consequences. Because if G does not influence the response, that means that the statocyte, the sensor, is not a stress sensor. It's not the weight of the grains that is filled. It's more certainly a position sensor, because when you incline, the final position of the grains, of course, will be at the bottom. So the position does not depend on G. And so that means that it really works like a clinometer, measuring the angle and not a stress, not an acceleration. So it's completely different from the inner ear that we have in mammifers. But if it's a position sensor, that means that in order to be sensitive, the grains have to move. So here I have a very naive movie. You just put grains in a viscous liquid. You incline at 15 degrees. Nothing happens. No motion, because you know that there is a critical angle for granular material to flow. So that means that there is no difference in position of the grains, so no response in the plants. So why, in all what we have measured, there is no threshold in the detection. The plant seems to be sensitive even at very tiny inclination. And so there is really a question here: what is the origin of the sensitivity of plants to small angle? And what is the origin of the sine law according to this position sensor hypothesis? So at this stage, we had to go and to look at the grains themselves to see what happened. So we designed a new experiment in order to look at the grains. So we just took a microscope, put it horizontally, in order for the rotation stage here to be in the plane of gravity. And then, so it's not easy experiment. It took us a few months to get the protocol okay. So we have to make a slice of the plants, to design a chamber in order to keep the slice alive for quite a few hours. And so we can do this, and at the end of this, we are able to get this kind of picture of the tissue. When you see here the different cells, elongated cells, so it's about 100 micron long, and all the dark spots that you see are pile of grains, of the starch grains, that are at the bottom of the cell, because we have kept this sample vertical. Now, look carefully. If I launch the movie, I incline, and you see. So I will play it again, but I don't know you have seen all the small avalanches in each individual cell. You can play again the movie. You see in the cell you have this motion, the typical avalanche motion that you have in granular systems. So from this kind of picture, we can go try to be more quantitative. So we make again image analysis to try to follow and to track the free surface of the pile in the cell, and to follow this angle here, and to try to get the dynamics. So that's typical measurement that you have. So that's, of course, noisy from one cell to another. So the picture is not so easy. But if you average over several cells, you get a nice average dynamics, or relaxation of the inclination of the pile. And two things. The first thing, if you plot now the inclination as a function of the log of the time, you clearly see two regimes. You have a first avalanche regime, like in a granular material, which is quite rapid. It lasts about 2 to 3 minutes here. And at some times, so that's down to 15 degrees, the inclination. And after that, we see a very slow motion, a kind that we call a creep regime, where you see the pile slowly relaxing toward zero, which means toward horizontal. So unlike classical granular material, here, what we see a pile of grains. We just relax toward horizontal. And that's the first, that gives you the first explanation why it may be sensitive, because you have a kind of liquid behavior here, that the pile is just going back to horizontal. So you can really create a clinometer here with this kind of grains. So of course, the question is why it's not a classical granular material. And so if you just go and look carefully, you see immediately. So you make a close-up of the grains. that the grains are not static, but you have an agitation that is inside the cell, that the grains are kind of agitated by something. And of course, you know that if you take a pile of grains and you now induce vibration, the pile will relax and reach horizontal. And so that's the same kind of thing that seems to happen with the statolites here in the cell, that you have an agitation that allows the grains to unlock and to flow and to reach the horizontal position. So of course the question now is, what is the origin of this agitation? And in the literature, in fact, there has been few studies about the agitation of the statolite. It's amazing. It's not linked to any detection of gravity, but there have been few studies. Some of them are just telling you that it's just thermal motion that can explain, because it's tiny grains, and it's few microns grains, that can explain the agitation. But some other study using some drug to get rid of, to change, in fact, the environment, tell you that it may be due to the biological agitation into the cell that is, and can create some agitation of the grain. So in order to decipher and to try to find out what is at the origin of the agitation, we decided to try to make some pure inert system, biomimetic system. And for this, we went to try to use some microfluidic technology, just soft lithography, to create tiny cavities like this, which have the same size as the cell in our wheat coleoptile, and to fill all the artificial cells with silica microbeads between 0.5 microns and 5 microns, in order to try to see how Brownian particles behave in such a geometry when you incline them. So typically, that's the same kind of picture that we have. Once you have succeeded in filling the cell, which is not very easy, but you see, and then you incline, and you see again the same kind of avalanche that is created and the relaxation of the pile. So the good things with this biomimetic thing is it really looks like the old Perrin's experiments, because you have a system which just is controlled by the competition between gravity, which tends to put the grains down, and the agitation, which is just trying to lift the particle. Except that here we are in a regime, in Perrin experiments, it was really agitated. Here we are in a regime in between granular and very agitated grains. But the good point is that there is a single relevant dimensionless number that controls this system, which is the Peclet number, which is just the ratio of the, let's say, the potential energy, just due to the weight of one grain. So mg r is the size of the particle, m is the mass of the particle, over kBt, which is the thermal agitation, the thermal energy that you include. And so that's really what controls the physics of this system. And the good thing is that because the mass is proportional to the size to the power 3, the Peclet number here is proportional to the size to the power 4. So it's very sensitive to the size of the particle. And so playing with particles between 1 micron and 5 micron, we are going to be able to study very agitated system and very cold, very granular, pure granular system. So that's one thing that's important. Second remark is that the viscosity does not come into play here. And so that will be an important point, because that will allow us to compare our biomimetic system with the biological system. So that's, for example, two movies with two different particle size. And you see a small particle. I don't know if you see well, but you see the agitation due to the thermal motion, which is much higher here than here, where you are using small, much bigger particle, just 2 micron and 4 micron, and you see the difference. And you start to see a difference also, that here you relax to horizontal, where here you still have a finite angle at the end. So with this system, we are able now to study properly what happened for an avalanche of a Brownian granular material. So first results, that's the same kind of curve. So we follow the inclination of the free surface as a function of time. We plot it as a log of time. And we found, let's look at the green curve first. We find again the two regimes. A first avalanche regime, rapid avalanche regime, followed by a creep regime, which is here. Here, what we are doing with the blue curve is just keep the same particle, same size of particle, but we multiply by 3 the viscosity of the fluids in order to just show you that, in fact, the viscosity doesn't play any role. It just stretches the time. So if you rescale now the two curves by this avalanche time, you just define an avalanche time at the end of the avalanche regime. And if you rescale them, you have exactly the same dynamics, meaning that in terms of the rescale time, the viscosity does not play any role, which will give us the opportunity to compare the biological system where we don't know the viscosity with the physical system. And now we can change the size of the particle. So just look, so the avalanche is not really changed by changing the size, but the creeping regime is really changed when you change a little bit the size of the particle. For the smallest particle, you have quite a creep regime which is much more rapid and seems to go to 0, where for bigger particles, you have something that never goes to 0, never reaches the horizontal. And so you can plot now here that the log of the time it takes to reach an arbitrary inclination, here we took 2.5 degrees, which is normalized as avalanche time, as a function of the agitation, the inverse of the Peclet. And the red point here are what we get from the pure Brownian system. And when you see that small particle it's not so long to reach almost the horizontal, where for big particles it takes forever to reach the horizontal. But now, on this non-dimensionalized plot, we can plot the data coming from the biological system, from the same avalanche that we follow in our wheat coleoptile. And what you get some points that are here. Meaning that for the same temperature, the room temperature, and with the size of the statolite, you have an avalanche which is 10,000 faster than what we will get if you take the same pure Brownian particle with the same size and the same room temperature. Which is a first proof that, in fact, here, the dynamics of the statolite seems to be really controlled by some biological agitation and not by pure thermal system. Another way to try to measure that is just to look, not during an avalanche, but you just let the particle follow sediment in the cell, and you just look at the free surface. You take the few particles at the free surface, and you track them using particle tracking. You see some jiggling around, they are jiggling around, and just you can measure the dispersion in terms of vertical motion, the delta Z, because of the thermal fluctuation, because of the agitation. And again, you can plot this delta Z normalized by the size of the grains as a function of the agitation. And for Brownian particle, you get this linear relation that if you are a small particle or very agitated media, you are vertically very agitated, where you are slow vertical fluctuation if you are big or low agitation. But now we can do the same in our biological system. And the data we get, it's very dispersed because it's biology and it fluctuates from one sample to another. But you see that in any case, we have all the data which are much above the pure Brownian motion, showing again that we have here a biological agitation and not a pure thermal agitation. So the last, and in fact, if you want to get back to this agitation, you need to have a temperature which will be 10 times larger. It's quite very hot. And the last things you can do to test this idea is to take, what we have tried to do, is to take those grains, cut the cells to get them out from the cell, so out from the biological agitation, and measure their agitation. And if you do that, indeed, you find that the statolites go back to the pure Brownian system here when they are out from the cell, meaning that the source of the agitation is really within the cell and the statocyte. So that's really one thing that now we have shown, that this agitation is really clearly not Brownian motion, but it's really come from biology. And what can be the source? So that's still an open question, but one idea is that it's come from the cytoskeleton. Cytoskeleton is an active gel which is constantly moving inside the cell. And so I'm just going to present you very rapidly a very preliminary result that we get in collaboration with Miyo Morita from Nagoya, who has designed very, very nice way of looking at the statolites And the good thing that she has been able to do that in different mutants of Arabidopsis. So Arabidopsis is really the fantastic plants where they have all the mutants you want. And they have some mutants where you have more or less actin, and actin is this polymers that create the cytoskeleton and the activity of the cytoskeleton. So we have not yet done careful experiments about avalanches and so on, but the only thing we have done is really just look what François Bizet and Mio Morita has done, is just tilted the cell upside down just to look at the sedimentation of those grains. And in fact, from the mean sedimentation, so that's a very crude analysis, but from the mean sedimentation, just looking at the Stokes law, you can infer what is the viscosity, the mean viscosity of the cytoskeleton. From the transverse agitation of the grains, you can infer what is the diffusion coefficient. And so, using the Stokes-Einstein relation, you can deduce what is an apparent temperature for those grains. And if you do that, indeed, what you see that we find that there are quite significant differences in the apparent temperature, depending on the mutant, and that the mutants with less actin has really lower apparent temperature, that means lower agitation, really, which is a good sign that the actin may be the source of the agitation in this system. So that's something that we need to go further in order to better understand and to do more specifically avalanches, real avalanches with this system. But that's really the first confirmation that the actin cytoskeleton play a key role in this dynamics. So at this stage of the story, where we are, we have shown that the statocytes are position sensor, work as a clinometer, because the statolite behave like an active granular material, and that's really what gives the sensitivity to this sensor. And that this activity and this agitation come from biological activity and not from Brownian motion. Just one remark to tell you that it's not so obvious, because if you have too strong agitation, you will have something with grains everywhere, and so it will not be very sensitive because you will not have any asymmetry in the cell to measure something. As the opposite, if you have no agitation, we have seen that you will have critical repose angle, so it will not be sensitive to small angle. So you see that there is a kind of trade-off where the nature are found, where you have enough agitation, but not too strong agitation in order to be sensitive and to have a clinometer based on the granular material. So that's something that's Of course, in order to finish the story, now I have to come back to the two classical laws that I have introduced to you about gravitropism, to come back to the macro scale, and to try to understand where does the sign law come from, and the dose response, where does it come from. So for the sign law, now that I've shown that the sensor is a position sensor, that the position of the grains that is important, we can propose something which is quite easy. It's just geometrical argument, because now if you incline such a thing, you see that if it's a position sensor, that means that what is important is the contact between the grains and the membrane. Okay? So if it's symmetric like that, you understand that there will be no asymmetric flux of the hormone. But now if you start to incline, you have an asymmetry, and the asymmetry in the contact between the grains and the two faces here is simply this length, which is proportional to the sinus of the inclination. So just from geometrical argument and knowing that it's a position of the satellite that is a measure, we can understand that at the Planck scale, we will have something that is proportional to sinus theta. So that's something that has to be, of course, we have to check about that and try to find some biological marker that will show you that. But that's what we can propose for the sign law. The second law is more difficult, because I tell you again, what has been done here is just experiments using transient stimulation and stipulating that the response is proportional to the intensity of gravity times the time of stimulation. So in order to better understand that, we have to do some experiments with transient stimulation. And so that's something that we have done. So the experiment is quite simple. No, with biology, no experiments are simple. But it's just you take your plants, you incline them 1 minute 2 minutes, 3 minutes, or what you want, and you come back to vertical, and then you follow them. They will respond or not, depending on what you have done. So if you do this kind of experiments, indeed, you find a response. So that's the different curve are obtained for different time of stimulation. So that's just the tip angle as a function of time. T equal to 0 is the time where you have inclined it. And you see that the longer you incline the plants, the stronger the response. And another point that you see that you have always a delay also in the response that I will talk to you later. So you can measure here again a response. You can quantify the response as a function of the stimulation time and see what happens. And indeed, you find something that looks like that depends on the stimulation times. If the stimulation time is too rapid, there is no response. The red dots here is the response we obtain for permanent inclination. So that's something that decreases like that. So with this, we are quite happy. We say, oh, but perhaps we can just explain this dose response with our idea of avalanche. Because the avalanche, the avalanche time depends on the gravity. And so if now you incline and the avalanche has not time to go up to the end, and you come back to vertical, the excursion of the grains will not be as long as for permanent inclination, and you will have a response which will be lower. And that could explain in the same picture, just with a granular avalanche, why you have this kind of things. And of course, that means that this curve should depend on gravity intensity, because the time of avalanche depends on gravity intensity. So we did this experiments. Now we are trying to do this experiment at 3G. So it starts to be quite tricky, because we have to rotate the plants and to put them on something that is also inclined few minutes. So we have to design a remote control. So that's Hugo Chauvet who did that, a remote controller to rotate the small box during the rotation. And at the end of all this, we find the same kind of response that is proportional to the stimulation time, but again, no dependence on gravity. So we were a little bit lost, because that means that our simple idea that this curve was just a signature of the time of avalanche was not true. So we just went back to the avalanche and see if mechanics is okay. So just measuring the dynamics of the avalanche at different g. And indeed, an avalanche at 3g is 3 times faster as an avalanche at 1g. So at least, so this again was not so easy, because we have to put the microscope on the rotating table. So that was not so easy. But indeed, we find that, at least at the grain scale, the mechanics is okay. The avalanche is controlled by G. So what happened? It was just a question of time scale. I plot here the response we had, so that the gravitropic response as a function of the exposure time here, on the same graph as the avalanche. And what you see is that avalanches are much faster than the time that seems to control this curve here. The avalanche is finished about after 2 or 3 minutes, or 1 minute even at 3G, whereas here it seems that there is another time scale coming into play, about 15, 20 minutes. That is a time scale necessary for the signal to build. And so what we put in evidence with this experiment is that there is another time scale in the system, which is certainly linked to biochemistry that take times to start when you have the avalanche. And so that means that we have to take into account here what we have called an integration process. And that gives us another piece of the puzzle for the whole chain of detection of gravity. And with this result, we end up with this cartoon that I'm going to show you that we propose to explain how does it work. So the cartoon is just you incline, you have an avalanche of the grains, which is detected here, but take time to you have an integration process. We have this delay, that means that you have some transport, and at the end, you have the time of growth that creates the bending of the plants. So that's really a cartoon that we have. That is true here under Earth gravity, because we have seen that the avalanche is much shorter than the time it takes to integrate and to build the gravitropic signal. So from this cartoon, we can write a simple theoretical model. I'm not going to go into the detail of the model to explain you everything, but it's just based on this idea. We have an equation describing the relaxation of the avalanche. The relaxation, this one, the relaxation of the avalanche is measured by something we don't know, but through an integration process where we put some exponential kernel here. So that means it takes some time that we call tau memory for the signal to build, to fully be constructed. And once you have the signal somewhere, this signal trigger the differential growth, and so the bending of the plants. And so with this kind of simple model that we can calibrate it because we have measured all the time scale that we have into the model, we are able, in fact, to more or less quantitatively reproduce the response of the plants, the microscopic response of the plants to the arbitrary stimulation that we are able to impose to the plants. And that's one thing. But the most interesting thing is that within the model, we can now play, and we can, in fact, unify all the responses that are known for gravitropism into a single phase diagram. So that will be my last result that I'm going to show you and try to explain you. That here we have a phase diagram where we have put here the stimulation time, and horizontally that's the avalanche time. So the gravity is here. If you change gravity, you will just control the avalanche time. It's controlled by 1 over the gravity. So short avalanche time, that's Earth gravity typically. And if you want to go to long avalanche time, you go to microgravity. So now, let's say that you are looking at experiments under Earth condition. If the stimulation time is long enough, longer than the memory time, that means that you fully built the gravitropic signal, and what you found is the sine law, simply this geometrical argument. But now, if the stimulation is shorter than the memory time, the time it takes for the signal to be fully integrated, of course, you will not get the full signal, and you have something that is proportional to the time of stimulation. That's what we observe in our transient experiments. But now, if you are doing the same if we were able to do the same kind of experiments in microgravity, in this case, the avalanche time becomes longer, and eventually can become longer than the memory time, which means that the limiting process is no longer the memory time, the time it takes for the gravitropic signal to build, but it's become the avalanche itself. That's the mechanics that becomes the limiting process. And in this case, of course, if the stimulation is short, you will get something which is proportional to stimulation time, but also proportional to the gravity, because the avalanche time is proportional to the inverse of gravity. And so you see that using the simple approach with all the ingredients we have, we are able to find the different regime and to put in a single phase diagram all what was observed before in the different experiments on gravitropism. So there is the last regime that I'm not going to discuss because we just predicted in the model, but in order to go there, you will have to go to experiments in microgravity about 10 minus 6. So I think nobody will be able to see if it's true or not. But that's the last point, that we are able now with our scenario to really unify and to rationalize all what we know about the response of gravity. So I'm going to conclude with the slide. So what we have shown with all this set of experiments, you see we have done experiments at the micro scale, at the macro scale of the plant scale, using biology, using mechanics and biomimetics system. At the end, we have first seen that the statocyte work as a position sensor. It's a real clinometer. That's angles that are measured in the plants and not acceleration, which is different from the inner air in our system. The sensitivity is possible because there is an activity of the granular media. We have an active granular media which allows the systems to be sensitive and to relax towards zero, to really be a clinometer. And this is thanks to the activity of the cytoskeleton of the biology. And at the end, what we have put also in evidence is that there is a hierarchy of time scale in this system with biochemistry that's come into play, of course. It's not just mechanics, but that the competition between all the time scales allow us to really rationalize all the observed response that was in the literature. So, of course, there is a lot still open question after this work, this story. First, I think one big question that is more in the biological side it's how are satellites detected in the cells. That's really something that we don't know, how the position of the satellites are detected. Secondly, we have designed a model which is quite simple for the detection, but now that can be used in more complex and more complex models that take into account the spatial variation. There are also models, especially for roots, that has been developed by Oliver, for example, taking into account the transport of auxin that will perhaps explain what we have shown. There is also proprioception. That's something I have not talked about, but which is very important, that plants feel their own curvature independently of gravity, and so they want to uncurve. So that's something that has to be taken into account if we want to really realistically describe the motion. And from a physical and fluid mechanics point of view, I think the system also opened new perspective and new questions that are not addressed in the literature about the behavior of Brownian granular media and what is the dynamics of those, the rheology of those avalanche in link with glassy transition and what is done in the physics community. So with this, I'm going to stop. And thanks, of course, most of the experiment has been done by Hugo and Antoine, really difficult experiments here. François and Mio for the biology and the work on the mutant, and Valérie Leguet, Yoel Forter from Marseille, and Bruno Moulia, who are really fine collaborators. And I thank you for your attention. And it's not yet.
Wonderful talk, Olivier.
Thank
so
you.
we've got time maybe just for two very quick questions.
You haven't talked much about the leaves, but I was wondering if you find also these cells in the leaves, if they orientate at growth, or they just stay perpendicular to the stem.
That's a very good question. In leaves, not much in leaves, but in branches, yeah, there seems to be this kind of, and that's really an open question because depending on the species, biologists have introduced what they call the gravitropic angle. Like if there is somewhere written that the angle was no longer 0, but 45 degrees, that the branch has to 45 or 90 for some species. That is written somewhere, and that just, we don't know where it is written, and how can we, that's something we want to check, how this picture and the scenario can now be. So there are very few studies about this, about auxin flux that will be in addition to this, that will create some steady state incline. But that's an open question.
In some of your pictures when you were showing the growth where the stem was bending, the bends seem very localized to a particular portion. They seem very sort of straight and bent. Are the cells localized, the straticized localized?
Okay, there's just one picture when you see that. So in most of the experiments I've shown you, on the width, in fact, a plant, there is a growth zone, which is at the tip, but which is not localized really. It's really a growth zone. And in the width coleoptile, where we have done all the measurements, the growth zone coincides at the time where we are doing the measurement, is everywhere. So it's just growing everywhere, and that's why it's growing everywhere. Here in this, just a picture that shows nicely the gravity, is lentilla that we have put, they were too long. They were long enough so that the growth zone is not the whole shoot. And so the bending that you see is just that all these parties were not growing anymore. When we start with them, they were this length, or something like that, and so they were inclined. And so that was a growth. There is a finite growth zone that you can take into account in some model, and so on. You're right, and that's just a measure of the growth zone, in fact.